fix scientific notation. And multiply or divide scientific notation. All right, so we're going to fix scientific notation. In other words, if there's something that's not quite right about it, we're going to be able to fix it. And then we're going to be able to multiply and divide. All right, so looking at this. Let's look at this first problem. 12.3 times 10 to the fourth power. What's not quite right about the scientific notation? Destiny, thank you for raising your hand. Yeah, it's 12.3 instead of, it should be something between 1 and 10. So this is not quite right, all right? This is not quite in scientific notation. This should be 1.23 times something. So the question is, that we really have to think about is, how do I fix this? What would I need to multiply 12.3 by in order to move the decimal the way it needs to go? What would I need to multiply 12.3 by to get the decimal to move where it needs to go? This is where a lot of that conceptual understanding of these multiplications of factors of 10 really come from. What do I need to multiply by? You say
Negative 0.1.
Yeah, well, not negative 0.1. 0.1, which is 10 to the negative 1. So the next question I really have to ask myself is, can I borrow a 10 to the negative 10 to the negative 1 from over here? No. Okay, so what we really need to do is we need to have 12.3. I need to multiply it by 1 over 10 so I can get it right. But I can't change the value of this. So what else can I put in here that's going to make this, whatever goes on inside this box, not change the value? Anadari. Not by itself, but by its reciprocal. Okay, so this is kind of like thinking about it this way. I'm not changing the value of the number if I'm multiplying by 10 and 1/10, because together they are 10 over 10, which is 1. So when I use the associative property, I look over here. This is going to fix it. I'm multiplying by 1/10. That moves this decimal once to the left, 1.23. And if I associate over here, 10 times 10 to the fourth, that's going to become 10 to the 10 times 10 to the fifth. I'm adding an extra multiplication of 10 in there. So 10 to the fourth is going to become 10 to the... So, I mean, let's take a second. Let's think about this as expanded out. This is now 10 times 10 to the fourth is times 10. Oops. Not 110. This 10 to the fourth is 10 times 10 times 10 times 10 times 10. This is really 10 to the fifth. So I fix my scientific notation, and I get 1.23 times 10 to the fifth. Now, what I'm going to guess that a lot of you are looking at this paper doing is you're coming up with a rule. I'm going to tell you right now, please don't come up with a rule. Please don't memorize a rule. The reason for that is because you're never going to remember it. I still can't remember it. I got ready to teach this lesson and I went, all right, what's the rule? I couldn't remember it. I went through and I made the lesson, and I did the lesson basically in my head, and then at the end I was like, well, what's the rule? And I couldn't remember it. Because the different problems are going to do different things. So you have to understand this concept of how am I going to fix it, and how does that change what's going on here. Can I borrow something or not? All right, so let's look over here at this other one. Looks very similar. What's wrong with this one, though? A little bit different. Isaac. Yeah, this one, it's too much to the left. So I have to figure out how am I going to move this one decimal place over. So what do I need to do to move that one decimal place over? Yeah, multiply it by... If I multiply it by a 1/10, it's going to move the other direction, right? It's going to make the number smaller. I need to make this number bigger, so I need to multiply by... Multiplying by 0.1 is adding an extra decimal place. What do I need to multiply by? 10. I need to multiply by 10. So I've got the 0.123, and I need to multiply it by 10. Good news. I have a whole bunch of multiplications of 10 over here. So I'm just going to break that 10 to the 4th up into 110 times 10 to the 3rd. So I've just taken that 10 to the 4th and I've broken it up. Because I'm borrowing 1 to fix this problem. Because I've got what I want, I just needed to move it over. So I'm going to associate those. That's going to give me 1.23 times 10 to the 3rd power. So as you can see, if you were trying to memorize rules, right now you've got 2 rules. You've got a rule for when the number's too big, and you've got a positive exponent, and you've got a rule for when the number is too small, and you've got a positive exponent. Okay? This problem right here was actually supposed to be a -4, so let's fix this one. Otherwise, it's the same problem. All right, so this looks the same as the problem above it, except it's got a negative, so make sure that you fixed it. It's supposed to be -4. But if you try to apply the same rule, it's too big, you're going to get it wrong. Let's talk about why. 12.3, what do I need to multiply it by to fix it? Jalela. 1/10. So I need 12.13 times 1/10 to fix it. Good news. Look at all these over here. This 10 to the -4, that's really just a whole bunch of multiplications of 1/10 because it's negative exponent. All right, make sure we understand negative exponents. That means we're looking at the reciprocal. So here that's 1/10. So I'm just going to break this apart. I'm taking off 1/10. And then I'm going to leave the rest of them over here. All right, so I can borrow that 1/10 to fix my problem. And then I can associate these two things. This is going to give me 1.23 times 10 to the -3rd. All right. So we can see that something different happens when it's a negative exponent and it's too big. This would be a 3rd rule that you would have to memorize. And all of the rules are so similar that you'd never be able to keep them straight. That's why I'm telling you, you can't just go through this and make an assumption about how to do it. Make the rule. It's going to be impossible to memorize. So look at the next one. I have 0.123 times 10 to the -4. I have 0.123. How am I going to fix it? Multiply it by 10. So I've got 0.123. And I need to multiply it by 10. Question. Can I borrow from these 10 to the -4th? No, because those are all 1/10. Those are all 1/10. All right, so got a whole bunch of those over here. What do I need to do to make sure that since I can't borrow, that this becomes a multiplication of 1? What can I do in there to fix it? Make sure that I don't change my value here. Anadari. Times it by 0. That would give me 10 times 0 is 0. That would change our value pretty significantly. Haley, what do you think? 10 times 1. That's still a net multiplication of 10 in the middle there. I need a net multiplication of 1. Kenneth, what do you think? Isaac, what do you think? Yeah, so I need a 1 over 10. All right, that makes that a net multiplication. So now I can associate these two things. This part fixes itself. This gives me 1.23. And here, when I associate on the other side, I'm multiplying a 1/10 times a whole bunch more 1/10s. So, if you need me to, I can expand it out. This is really like 1/10 times these 4 more 1/10s, 1/10 times 1/10 times 1/10 times 1/10. How do I write this in scientific notation? Najari?
1.23 times 10 and the power of 5. Wait.
No, right idea. 5, but there's a problem with that because these would make these multiplications of 10. I need them to be multiplications of 1/10, so I need to make it negative. All right. So again, if we think through that, again, this would be 4 different rules you have to memorize because different things happen when they're too big and they're positive exponents, when they're too small and they're negative exponents. It's 4 different rules you have to memorize. So you can't really just memorize it. You kind of got to think through the process. Let's look at one more. 123. Okay, now this one's definitely wrong. How many places do I need to move the decimal? 2 places. So I need 2 multiplications of 1/10. All right, so I have 123 times 1/10 times 1/10. Can I borrow any of the 1/10ths from 10 to the 4th? Keep yes or keep no. Can I borrow any 1/10ths from 10 to the 4th? You should be telling me no, because 10 to the 4th are multiplications of 10, not multiplications of 1/10. So if I want to fix this and make this a net multiplication of 1, what do I need to do? For each of those 1/10ths, I need to multiply a 10 over 1. So times 10 times 10. Times 10 to the 4th power. All right, so this all cancels out. Sorry. Scratch that. Go back, go back, go back. All right, whatever. This associates and fixes our problem. This becomes 1.23 because those multiplications of 1/10 move the decimal 2 times. And this associates and I have added 2 more multiplications of 10 to my 10 to the 4th. So now I have 10 to the 6th power.
I get this now.
All right, one more. Now I have 123 times 10 to the negative 4. Where do I need to move the decimal? Twice to the left, which means I need 2 multiplications of 1/10. I need to make the number smaller. 123 times 1/10 times 1/10. Can I borrow these multiplications of 1/10 from the 10 to the negative 4? Yeah, these are 10 to the negative 4. So these are a bunch of multiplications of 1/10. So I've got those two multiplications of 1/10. And that's going to leave me with how many multiplications of 1/10? 2. So 10 to the negative 2. So this is really, I just took this and broke it up. This is just broken up. We can associate these two. This fixes our problem. 1.23, the multiplications of 1/10, move the decimal 2 times to the left. And this leaves us with times 10 to the negative 2. Yoel.
Can you just and then wouldn't it be easier? Wouldn't it be easier if you just moved it to the side, say twice, and then just took it away, 2 on the.
I mean, that's essentially what we did.
But either way to do it.
No, this is as easy as it gets. I mean, there would be an easier way if you memorize the rule for all 4 different things. That would be easier because you would have less steps to do, but it's not easier because trying to memorize 4 different things that are almost exactly the same, you'll never keep it right in your head. I'm positive. All right? So, there are 2 essential questions when fixing scientific notation. Number 1, what do I need to do to move the decimal? And 2, can I borrow that? All right, so just looking back at those last 2 problems, our first question was, what do I need to do to move the decimal? And our answer was multiply by 2 1/10. The next question was, can I borrow those 2 1/10 from my 10 to the 4th? The answer was no, because 10 to the 4th is multiplications of 10, not multiplications of 1/10. So when the answer is no, we have to fix it like this. When the answer is yes, like over here on this one, we can just borrow those 1/10 by splitting it up. All right? This requires deep conceptual understanding of scientific notation. I'm crossing my fingers, and it sounds like most people in the room have that deep conceptual understanding. It also requires deep conceptual understanding of associative property and exponents themselves, and the inverse property. So what you see here is like all of these understandings that we've learned a long time ago that we kind of took for granted as being like, oh, these are like really simple things. And then maybe we didn't quite memorize them the way that we should or understand them the way we should, are now coming back to bite us. So hopefully, this is a lesson to you. Everything that I teach you will come back. Everything that you have learned is really just a small step to a bigger problem. All right. We've got a couple of, our second half of our lesson today is what happens when we multiply and divide scientific notation. So we've got a couple problems to kick us off over here. This first one is a word problem. It says Jupiter has a mass of 1.8986 times 10 to the 27th kilograms. Mars has a mass of 6.4185 times 10 to the 23rd kilograms. About how many times more massive is Jupiter than Mars? So we want to figure out how many times bigger it is. So we can figure this out by taking the bigger one. It says about, so I'm actually going to round here. I'm going to make this 1.9 times 10 to the 27th. And I'm going to make this a approximately 6.4 times 10 to the 23rd. Now here's the great thing about scientific notation. It makes this a whole lot easier. This is like one fraction. This is like another fraction. I have 10 to the 27 over 10 to the 23. All right, well, that's easy. I know this is 10 to the 27 minus 23. This is using our exponent rules. Now think about what this would look like if you didn't have that 10 to the 27th. You'd be writing out 23 zeros when you were trying to do this multiplication. And that's just for the top number. That's just for Jupiter. You'd be writing out another 19 zeros for Mars. But instead, we get to do this nice, wonderful little exponent rule, which tells us that in the end, we're going to get times 10 to the 4th power. Over here, though, we have to remember that we have this 1.9 divided by 6.4. And I'm going to give you easier numbers and real problems, but I'm going to tell you that this is approximately This is approximately 0.3 times 10 to the 4th. Now, there's two different things we can do, and it really just depends on how they want our answer. If I just want to know in standard form how many times bigger it is, we can just turn this now into standard form. Really easy, right? Yeah. Take 0.3, move the decimal 1, 2, 3, 4 times. This tells me that Jupiter is 3,000 times more massive than Mars. About. Thank you. Let's put my little squiggly in there. It's about 3,000 times more massive. Or what if it needed to be in scientific notation? How can I fix this? 0.3 times 10 to the 4th. Well, I need a multiplication of
3.0 times 10 to the 3rd power.
So let's think about how we fix this problem. Yeah, I think that's right. Let's think through the process though. What do I need to do to fix the 0.3? What do I need to multiply by to fix the 0.3 for scientific notation? Yeah, it's a multiplication of 10. 0.3 times 10. Can I borrow that 10 from over here? Absolutely. So now that means that we're left with 10 to the 3rd. So I get 3 times 10 to the 3rd. It depends on what's your answer to be. Today, in real world problems, I want you to give me standard form. If it's not a real world problem, I want it in scientific notation. Okay? All right. Got one more real world problem here. This says the mass of a red blood cell is approximately 9 times 10 to the negative 14th kilograms. The average human has about 2.5 times 10 to the 13th red blood cells in their body at any given time. About how much do the average human's red blood cells weigh? All right, and then it gives us some extra information. Right now, we're just going to be able to find it in kilograms. So if I've got a whole bunch of things that weigh this much, and I know how many there is, what do I need to do? What's my operation here? Yeah, I need to multiply. So this is 9 times 10 to the negative 14 times 2.5 times 10 to the 13. So we're going to figure out if, giving all of your red blood cells away would be a good weight loss program. Let's figure it out. Probably not because you die. But let's figure out how much weight you would lose. All right, so this is where we see this is a string of multiplications. Thanks to the commutative property, I can just make this 9 times 2.5. So I've just commuted 9 times 2.5 times 10 to the negative 14 times 10 to the positive 13. Now I can associate. 9 times 2.5. I'll save you the trouble. That is 22.5. And here we have multiplication of exponents. What's our rule? What's our rule? What's our rule for when we have multiplication of exponents with common bases? You did this on your do now this morning. Stephen? Add the exponents. So 10 to the negative 14 plus 13. This gives me 22.5 times 10 to the negative 1. And this is really great because actually if we put this in standard form, it fixes our problem here. All right, so we move the decimal over one time and tells us this is equal to 2.25 kilograms, about 2.25 kilograms. And if we wanted to figure out how many pounds that is, that's 2.2 pounds per kilogram. We get something along the lines of approximately 4.5 pounds. Hey, that's some good weight loss for, just letting all of your red blood cells out, right? Nobody wants to try that?
No.
All right. All right.
Well, you already getting one.
All right. So let's look at a couple more examples here of just what this looks like outside of the context. So again, I'm going to look at this here. Nice and easy. When it's division, I can just associate this and associate this. I have 10 to the 4th divided by 10 to the negative 2. So we have 1.2 over 3. I'll save you the trouble. That's 0.4 times 10 to the 4th. Since this is a division, our rule is to subtract. Leave change switch times 10 to the 6th power. But we got to fix this.
Why?
Because this is not quite right scientific notation. So what do I need to do to fix the 0.4? Multiply it by 10 or multiply it by 110?
By 110 because it's negative.
Multiply it by 10. 0.4 times 10. And then the next question is, can I borrow that 10 from what I already have? Keep yes or keep no. Can I borrow that 10 from what I already have? Yeah, these are positive multiplication set of 10. So this would be, I borrowed one of them. That leaves me with 10 to the 5th power. So associate this. 0.4 times 10 is 4 times 10 to the 5th power.
That's not 4, that's 4.
All right? And let's do one more multiplication. So here with the multiplication, again, this is just a string of multiplications in a row. So I'm going to use commutative property. 1.2 times 3 times 10 to the 4th times 10 to the 2nd. All I've done is use the commutative property here. Now I can associate 1.2 times 3. That's 3.6. Times 10 to the 4th times 10 to the 2nd. That's 10 to the 4 plus 2, which is 3.6 times 10 to the 6th. Is this proper scientific notation? Yes, this is proper scientific notation. This number is between 1 and 10, so we're good here. All right? Questions? I think that the division and the multiplication is so simple that I'm not going to bother going over these last two problems. Let's move on to our together.